Alrighty, so can you see my beautiful paint screen?
Yes.
Awesome. Today we'll be doing graphs, and they're a bit similar to trees, but not really. They're still a data structure, useful stuff, and you'll find it in a lot of problems and real world problems as well. We're going to be discussing about that in a jiffy. But yeah, today we're going to be talking about graphs and how to represent them first, and how to traverse a graph completely. So this is going to be our two main topics for today: graph representation and graph traversal. Now, a graph is basically a data structure which is formed out of nodes. You can see all these nodes: A, B, C, D, E, F, and G. And on the right side, you will have one way to represent such a graph. Now, you can imagine these nodes as being cities, maybe, and the links between them are called edges, and they represent the roads from one city to another. Now, in this matrix on the right, hope you guys see it properly, we have the distance between each node and all the others. And I'll help you a bit here. Each column and row represents, so this column A, the first one, the first row actually represents the distance from A to each other node. So from A to A, position 0, 0, that's the distance from A to A. Position 0, 1 is 12. That is the distance from A to B. And you will see that this matrix is symmetric, based on and relative to the first diagonal, right? So you can see that you can find 12 here, and then 12 is also here, and I should have the smaller, and then 11 is here, 11 is also here, 16, 16, and so on and so forth. You can find that everything is symmetric based on this diagonal. And of course, this diagonal will always be 0, because the distance from every node to itself is going to be 0. So let's just put these down as to add a bit of clarity. E, F, and G. And also maybe here, A, B, C, D, E, F, and G. Okay, great. And now you can see that the distances are clearly visible. Now let's put some edges here on our graph. And we can see that the distance between A and B, so there is actually an edge between A and B because the distance is 12. And we'll just write this edge here and add a 12 on it. And then there is also an edge from A to C. So we'll add it here, A to C, and then add the distance here. It's 11, A to D, A to E, A to F, and there is no edge from A to G. Now allow me to not add all the edge distances on all of them. They're not really that relevant this lab. They'll be more relevant in the next one, and I'll explain why a bit later. Now again, let's go to the second line, the distance from B to every other node. We've already treated this case, so the distance from A to B is equal to the distance from B to A. That's still 12. It's not always the case that if you can go from A to B, you'll be able to go from B to A. But this is, again, something which we'll discuss next time when we'll be discussing directional graphs. This is not a directional graph. This is basically a graph, a bidirectional graph, because if you can reach any point from any other point, then you can also go back. And yeah, anyways, let's move forward. From B to A, it's already on there. From B to C, there's also an edge. From B to D, there is no edge because we have 0 here. From B to E, also no edge. From B to F, no edge. And there's one from B to G, which is of length or weight 2. Okay, let's go forward. From C to A is already done. From C to B, already done. From C to C, no distance. From C to D, there is an edge of length 3. From C to E, there is also an edge. And from C to F, there is no edge. And from C to G, there is one of weight 7. Now from D, we know for sure that everything until D, until itself, is figured out because we previously filled them out. And then there's one from D to F. There is no edge from D to E. There is one from D to F of weight 5. So D to F here. And there is one from D to G of weight 8. And there's this one. All right, there is E and EFG left. So from E to F, we have weight 4. So there's an edge. And from E to G, there's nothing. From F to G, there is nothing. That's the last one we'll check. And the G to everything else should be already filled. All right. So we have all the edges already there. Let me just remove this, this number here because we're not going to be dealing with those. And let me ask you if you have any questions up until now. Is everything clear how we represented this graph in a matrix form?
Yes.
Yeah.
Yeah. No questions from anyone, okay? Everything is fine and clear. Great. There is one more way in which you can represent a graph, and that is in a list form. This is going to be your homework, but I'll explain it right now. Instead of having a matrix, you will have this. You will have a list, for example, A, and then after A, you will have, let me think how you could most easily represent this. Maybe something like A and then B12 and then C11 and then D9, and so on. And then B, and you'll note all the neighbors which you'll have. So this is basically representing it as a list. You can find your own convention. It doesn't really matter all that much. There's plenty to go around on the internet. This is just one example in which you don't represent it as a matrix, but you represent it as a list. So you have a list with as many nodes as many entries as nodes, and each entry contains basically a list in itself, and that list contains the neighbors and the lengths or the weights of the edges for each neighbor of A. So let's just fill this out, and we have an edge from A to B, C, D, and also E, which is E7 and F6. And that's it, right? All the neighbors of A are represented here. And then all the neighbors of B will be represented just quite the same here. From B to C, there's 16. And from B to D, there's nothing. And then there's B to G. And that's 2. And so on. I'm not going to fill everything up, but you get the gist of it. This is going to be your homework. Basically, just representing this graph as a list, not a matrix, and switching from one to the other. Okay, now, is everything clear so far?
Yes.
Yes.
Great. Awesome.
I have
No.
one question.
Go ahead.
Does it need to be a list of lists, or can it be just an array of lists?
It can be an array of lists. It doesn't
Okay.
matter. Yeah, of course, of course. Because you'll know in advance, at least for the things which will implement, you'll know in advance how many nodes you'll have. That means you can allocate a simple array and then put everything there. And that array will basically contain each array element will contain the list of neighbors. So that's fine. You can use that as well. All right. Now, is there anyone who did not hear about breadth first search and depth first search? I'm assuming that's a clear yes. I mean, no from everyone. Everyone has heard about it. So let's try to trace that algorithm. Let's BFS pseudocode. Let's search for that. By the way, can you still see my paint, or are you looking at something else right now?
Something else.
Okay, good. So I'm just grabbing this pseudocode and putting it here. Whoa. Okay. Now this is the pseudocode for breadth first search. Can anyone tell me what is the specific of breadth first search? How it works, at least conceptually, and what it does, first of all?
You choose a starting node, and then you visit all its neighboring nodes before moving in more depth.
Yeah. So basically the point of all these, both breadth first search and depth first search, is traversal, traversing every possible node of a graph. Breadth first search does it in one way, depth first search does it in the other, and the only difference is, as you said, in which order do we take the neighbors of the starting or of the current node we are visiting. Now, let's trace this pseudocode and see what we get. Let's assume that our starting node is G, for example. Let's read this. Let Q be Q and NQ S. S is the starting node. So at this line over here, we use a Q and we NQ S, and that S is, in our case, G. We mark G as visited, and let's assume we mark those things like this. No, let's put another color. Can you just hide? Just go away. How do I make this go away, by the way? This bar on top, I hate it. Hide floating mean. There we go. Okay. So we mark G as being visited. And we are over here right now. While our Q is not empty, and it is not because it contains G, let's represent our Q as well. So this is our Q, and right now our Q contains G. Q equals G. Okay, removing that vertex from the Q whose neighbor will be visited now. What will I get when this executes, by the way? What is a V gonna be here? It is far from being a rhetorical question. I need an answer. What is V here when I execute this DQ?
It's G.
It's G. Good Lord. Yes, finally. And here I take all the neighbors W of G. What are all the neighbors of G?
B, C.
B, C, and D. Thank you. So here I will have B, C, and D, and they're taken in lexicographic order. This is fine. It doesn't matter. Okay, so first off, if we are taking them in lexicographic order, what is W here?
B.
It's gonna be B. Okay. And we NQ B, okay? But we forgot something. Here, once I DQ it, then my Q will no longer contain G, so I have to delete it. Okay, great. So I have to NQ B, so then my Q will contain B. And then I mark B as visited. And that's gonna be done like this. Great. What happens next? What value does W take next?
C.
Yep, it's gonna be C. So I NQC, I delete it from here. I NQC and add it here. And then I mark C as visited because of this line over here. This one here. And then I do the same thing for D. I end up marking it as visited and putting it in the queue. Oops, that's a bit far. Whatever. And then it gets deleted from here. Alrighty. Now what happens and what do I do? And where do I end up in this code? Tell me.
At the while?
At the while, yes, of course. So I'm done with this because I treated all the neighbors of G and I end up here again. What value does V take?
B.
B. So I DQ it. That means I get to remove it from here. And then I end up here. And what are the neighbors of B?
A, C,
Yes.
A and C,
No.
and G.
And G. Great. So then, what happens here? Which is the first node? W. A. It's going to be A. Okay, and luckily A is not visited because I didn't color it. So I enqueue it first and then I mark it as visited. So let's first enqueue it. That means it's going to end up at the end of the queue, not at the beginning. I'm dealing with a queue, not with a stack. Remember that. It's going to be important. And I delete it. And finally, I color it. Whoops. There we go. Now what happens next? What about C and G?
They are ignored because they are already visited.
Yes, they are ignored because they are already visited. So both of them get to be assigned to W here, but they're ignored because they're visited and nothing happens. So they just swoosh out. Okay, what happens next? Tell me.
B gets C.
V gets the value C. So C gets DQ'd. And by the way, maybe we should print these in order of visiting. Let's print the output here. So we first visited G, and then we visited B, C, D, and A. And then we'll see what happens next. So yeah, which one was now chosen? It was C, right? So V gets the value C, and now we get all the neighbors of C. What are all the neighbors of C?
BGD.
No.
B, A, G.
Tell me
E.
in, yeah, just let's be consistent and get them in lexicographic order.
A, B, D, E, G.
Yes, E and G. Good, great. Alrighty, so we know for a fact that A is already visited, so we do nothing, we just remove it. Again, we know that B is already visited, nothing happens. D is already visited, nothing happens. However, E is not visited. So then E gets to be enqueued, so it ends up at the end of the queue. And let's just write it here as well. So it's E, whatever. And I color it. Great. And G is also visited, so I don't need it. Good, great. What happens next?
V becomes D.
V becomes D because we dequeue it, so we delete it from here. And now we get all the neighbors of D. What are those?
C, F, G.
Lexicographic order.
A, C, F, G.
A, C, F, and G. Okay, what happens next?
W becomes A.
Mm-hmm.
But it is visited, so we don't do anything.
Yep, correct.
Then W becomes C, the same,
Yeah.
we don't do anything.
Yep.
W becomes F, and we enqueue it.
So finally, we get to enqueue something here, F. And we actually have to color it and mark it as visited. Great. And how about G?
We don't do anything.
We don't do anything with it. Great. Okay. Now, what happens next?
V becomes A.
And?
We dequeue it.
Yeah.
We go to its neighbors, which are B, C, D, E, and F.
Yep.
But all of them were visited before.
Exactly. So we go to, V now gets the value E, and E's neighbors are all visited as well, so nothing happens. And then finally V, so we are finally here with our last node. V gets the value F, and nothing happens because all of F's neighbors are also visited. And this whole thing finishes because our condition in the while loop was while our queue is not empty. So we exit. And this was the outcome. This was the result. G, B, C, D, A, E. This is the result, and this is the order in which, in this breadth first search, all the nodes.
We should also add F.
I'm sorry. Yes, we should. I forgot about that. There we go. Now, this is the order in which the nodes, all the nodes of my graph, were visited based on this breadth first search algorithm. Any questions so far? No, nothing. Okay, let's do the same thing, but with a depth first search. So I'm gonna undo everything, and there we go, close. Yeah, and now search for DFS pseudocode. Okay. What, good Lord. No, I don't want the implementation. I want just, is this? Yeah, this is the recursive implementation. I don't want that yet. Let's search for something else. Oh, there we go. Perfect. It's the same format. Oh, this is the recursive one as well. But this is what I want. Okay. Finally. So now, instead of using a queue, and this is the only difference between breadth first search and depth first search, instead of using a queue, depth first search uses a stack. And let's see how this impacts our search. We'll still start from G, which is going to be our starting node, and let's go through the pseudocode a bit and see what happens. So let S be a stack. We initialize the stack, and in the stack, we put our starting node, which is G. So our stack initially contains G. Great. And we mark it as visited. Okay. So while our stack is not empty, we pop it. And what value does V take here? Just making sure you guys are paying attention. Tell me.
G.
G, what? You said G, right?
Yep.
Yeah, okay, good. So V is G. And we pop it. And we push all the neighbors of V in the stack that are not visited. And we mark them as visited. So all the neighbors of G have to be pushed in the stack if they're not visited. And because we are in the first iteration, they're all unvisited. So what ends up being the stack or in the stack? Tell me.
B, C, D.
Right, B, C, and D. Am I missing anything? No. And they're also all marked as being visited. So B, C, and D. Great. Now, let's go back here. So we are back here again. And what is the top of the stack now?
B.
What? Yeah, so the top of the stack is, no, are you sure it's B? Because I'm not. It's a stack, it's not a queue. What was
D.
what?
D.
It's D, because we always get the last element which was inserted. So we don't take the elements from this, because that was the order in which we entered them. We actually get them from here, from the other side. So maybe a more correct way to represent this stack, in a more obvious way, would be to write it like this. So it's B on the bottom, and then C, and then D. Because I first added B, and then I add things at the top, I add C, and then I add D above that. And we take the first element from here. So we take D out, and then we pop it. Okay, and we take all the neighbors of D which are not visited. Which ones are those?
A and F.
A and F. Okay. And we add those to the stack. So first we add A, and then on top of that we add F. And this is how our stack will look like. And they're going to be marked as visited, A and F. Now let's print out the order in which I'm going through this. So I've had B, I had G, I had B. And what happens next? Which one's my next node? What do I take next?
F.
F. Yes, I pop it, and then take all the neighbors of F which are not visited, which is, hello?
E.
E, yes. And then add that to the stack, and that's going to be added on top. So that becomes the first element. So I add this F here, and now what happens?
V becomes E.
Yes, V becomes E, but nothing else happens after that because all of E's neighbors were visited. So we just add E here and we pop it from the stack. And then the same thing happens with A, and the same thing happens with C, and the same thing happens with B. And finally, my stack will be empty, and the traversal will be this: G, B, F, E, A, C, and B. And that's quite a bit different than what I had before, because before I had this order. Let me just write it down. Before I had G, B, C, D, and then A, E, and F. Am I right? I hope I'm right. I should be. Yeah. So this is quite a bit different than our breadth first search result. And what we're going to be doing now is, oh, fuck. Hello? Yeah. You guys hear? Because sometimes Zoom just stops the call without noticing me. Actually, now we're going to be implementing everything, and I'm going to stop the meeting because I have to restart it every 40 minutes. because Zoom, and I'm going to give you the new link again, okay?
Okay.
Great, great. There we go. Okay, so we are gonna implement 3 methods today. I'm gonna first go through all this, through the whole project, because I've written a few things already, but I just left out 3 things which I want us to implement today. So the first one is a breadth first search, BFS. Second one is DFS, the depth first search, and then the third one is a recursive DFS. Now, let's go through all of this and see what we have already here. Now, this main function is very simple. It just opens up a file, matrix.txt, and this contains basically what we already analyzed. So it contains the graph which you saw here. And it reads the things from there. And this read from adjacency matrix, and that's called an adjacency matrix. This is coming from the file graph representation. And this graph representation also has a header, and you can find it here. It has a few methods: read from adjacency matrix, print the adjacency matrix, get number of neighbors of vertices, and get all neighbors of vertices. And we'll be using them in our BFS and DFS methods. Now, the read from the adjacency matrix is quite simple. We just use fscanf first to read the number of nodes which we have, this one, the 7. And then we allocate the matrix. Of course, I didn't put it in a different method. I just thought it was a bit of an overkill, but never mind. And then for each element of that matrix, we basically just read everything from that file in order, and that's it. Okay, it's really no biggie. Okay, and there's also a print adjacency matrix method, which just prints it in a more pretty way, because instead of using instead of just printing the values, I also print the corresponding node names, so A, B, C, D, and E, F, G. And let's just see how this print adjacency matrix looks like. There we go. So we have our columns A, B, C, D, E, F, G, and our rows, which is basically the same thing. And then we print out our values here. Now
you submitted a few. It looks quite.
I'm sorry?
Can I what? When I tried.
Yeah. Let me see. Font size, and maybe this. No, not here. Good Lord. I need this here. What? Can you see it better now?
Yep.
Great. Okay. So this is in the console. This is how it looks like. It's basically the just what we already have here. And the reason for which, if you asked yourself, the reason for which I just put 2 zeros here and 09 here is just so I can align these properly. So I didn't want to do this because, well, they're properly aligned, but they're missing some digits, and it doesn't really matter. You can use whatever you want. Okay, now I've also implemented a get number of neighbors of vertex, and a vertex is basically a node. Okay, this is the same name. So we have nodes and edges, or vertices and edges is the same thing. Vertex equal node. I first check whether or not V is smaller than number of vertices. And this number of vertices, I didn't tell you, this is initialized here in read from adjacency matrix and is a global variable located in graph.h. And this is the header file for our graph. And this simply contains 2 constants, unvisited and visited, 0 and 1. It contains our adjacency matrix and the number of vertices well, the number of vertices of our graph, and that's it. By the way, I completely forgot about this, so I realized it when implementing all of this. If you put everything inside the header file between such if not defined and defined tags, then you won't end up with multiple declarations of whatever errors. So that was the whole secret to all that. I'm sorry I didn't tell you before. I completely missed it, and I knew about it, but I forgot, and then I remembered it. And yeah, so you'll see that every .h file, for example, edge.h, everything is put between, and this is extra, everything is put between these if and def and define tags. And what this does, and in case you don't know, whenever you have such an include graph representation.h, compiler basically copies everything that is inside this header file and puts it here where it is included. Now, in case you include this multiple times, then the compiler will basically, and you don't have this tag, the compiler will copy it and put multiple copies of the same thing here. Or in case this graph representation.h is also used in graph traversals.h, so I put this here, it will copy it here as well. And then I end up with two of these graph representations.h in main. And that's really bad. That's not what I want. So these tags make sure that you only get to define it once. And in case it's already there, we don't put it anymore. So this is what they do. Very useful stuff. You'll see the code already on Git. Never mind. Okay, let's move forward. That was a parenthesis, a rather long one. So get number of vertices, get number of neighbors of vertex, actually. Code is pretty obvious and simple. We iterate through our matrix, and we just need one line from that matrix. If V is our vertex, so for example, our vertex is either 0, 1, 2, 3, 4, 5, or 6, because I have 7 vertices from A to G, and A starts from 0 and G is basically 6. So for we check the adjacency matrix's line number 6. Let's say we want to check G's neighbors, and if the value is bigger than 0 and I is different than V, that means that I won't consider G a neighbor of G, okay? Then the number of neighbors gets incremented, and I finally return the number of neighbors, okay? And there's another method here. It's called, another function here. It's called get all neighbors of vertex. And it's very similar to this one. Instead of just returning the number of neighbors, we also return, we actually return an array with all those neighbors. So first, I compute the number of neighbors, which it has. I allocate an array of that size, and I fill it up with the neighbors of that node. So for example, if G's neighbors are B, C, and D, right, then that array will simply contain, well, in this case, 1, 2, and 3, because B is mapped to 1, C is mapped to 2, and D is mapped to 3, okay? These values here, not very relevant today. They will be relevant tomorrow. Not tomorrow, actually, next time. Well, we'll be doing something else. Okay. So these are our graph representation methods, functions, and they basically just read from the adjacency matrix, print it, and compute some number of neighbors and all the neighbors of a vertex. Okay. with those things in mind, we can start implementing our BFS and DFS recursive functions. Yeah, we have graph traversals.h, which we didn't go through yet. It just contains these macros for our functions, DFS, BFS, and DFS recursive. And what I didn't yet show you, and I'll just briefly skim through, is the fact that I already implemented a queue and a stack. And this queue will have just NQ, DQ, peak, and is empty queue. And also will contain a queue variable. Here, I will have the actual implementations of these methods. So NQ, DQ, and peak, and is empty. There's really not much to it here. You'll be able to find this code on Git. I'm not going to waste any time right now implementing it because you already implemented the queue and the stack. I just did it again by myself. It's the same thing for the stack. Each one of these has a global variable called Q, and you can find the same thing here, a stack, which will be initialized when we need it in our DFS and BFS methods. Whew. Okay, great. Now, let's start off with our BFS. So close everything, go to Traversals. Is everything pretty much clear at this point, by the way?
Yes.
Yeah.
Yes? Okay. So I've written a bit of code just so we don't have to waste time on it right now. It wasn't really relevant. Now we have this, where is it? Now we have this pseudocode. Well, this is DFS, but we had it for BFS. Hopefully you'll remember it. First off, actually, let's just go and get it again, because it's worth looking at it while implementing. So we okay, and put it here. There we go. So I'm just gonna go from one side to another. We first initialize a visited array because we don't have that yet. So let's just put this here in visited, and initialize it like a simple array. Malloc size of number of vertices times size of int. Okay. And this should be size of. Okay. Why are you here? There we go. Okay, and then we need a few more variables, an iterator, v and a w, as far as I remember from here. So we need an iterator, v, which is going to be the current node, and w, which is going to be neighbors. And we have to mark everything as not being visited at first. So for our I equals to 0, I smaller than number of vertices, I plus plus, we mark visited of I as unvisited. And remember, please, this unvisited is a constant defined in graph.h, so it's equals to 0. It can really be whatever. So I mark everything as unvisited, so all our neighbors are marked as unvisited. Now what happens next? We have to mark our starting node S as visited. So I am here right now. So mark, how do we do that? Visited of start node equals to visited. And this visited is, again, in graph.h, and it is just the value 1. What comes next? Well, what I want to do is, I forgot to enqueue it, by the way. So enqueue start node. There we go. Mark is as visited, and I want to print it as well because I want to see the result of my BFS. So printf C and a space and start node plus A, and everyone understands why I did this, right?
Yep.
Okay, good. Basically, I want to print out the letter, not the node number, which is 6 for G. I want to print out G, and this is why I'm adding a big A here. Okay, moving forward. While not is empty Q, and I have this method, luckily, already implemented, I have to peek at this Q. So V becomes peek Q of content. Now, take a look at this Q first. Whenever we enqueue something, we create a node. So this creates the queue first because it's empty. And this create node function hides within node.c. And this node T is basically a structure which you've seen before. It has a content and it has a next. And I'm reusing this node both for my stack and my queue. And in queue, I just create this node in case the queue is empty, or else I add it to the queue. And this aux is basically gets the first value of the queue, and its next value becomes the create node of content. So an element always gets added in the end of at the end of the queue. Okay, and this peek, this returns Q, but this Q is of course a node, an array of nodes, basically a list of nodes. I'm sorry. So if I return Q and I peek it, so I peek it and return the content, this content will actually be the current node which I have to take. So the first node of the queue, and then I dequeue it, and this removes it. And am I in tune with our algorithm? Yes, I am over here. And now I have to do all this. So for all the neighbors is W of V in graph G. If W is not visited, I enqueue it and I mark it as visited. So how do I write that? It's pretty straightforward. I have two methods which I need, and they're already implemented luckily. So int number of neighbors is equal to get number of neighbors of vertex V. And I also need the actual neighbors, so neighbors. And this is going to be equal to get all neighbors of vertex V. And for I equals to 0, I smaller than number of neighbors, I plus plus. Here, sorry about that. Here, W becomes neighbors of Y. Oops. And if visited of W is equal to unvisited, so if our node W is not yet visited, first off, we print it out. So I use the same thing as here. And instead of start node, I put W. And then I enqueue it, enqueue W, and then I mark it as visited. So visited of W equals to visited. That's it. This should be all my, what is this? Why are you? Huh? Ah, oh, I missed that. That's all I need. Okay, so this is BFS. This is all the implementation, and let's just see if it works. And main, and instead of starting from the first node, let's just start from the 6th node. And could we make this easier? Yes, I think we could write something like this. A plus a G. No, this won't work properly. Whatever, let's just, whatever, 6. And let's see if the result is what we had previously got. So GBCDA E, and F, and G, D, C, D, A, E, and F. This was our BFS, and this is what we got in our code. Okay, let's go back. Is everything clear? Did you guys understand what I did here?
Yes.
Yes.
Okay, no questions whatsoever? Are you sure? Okay, so then let's move on to implementing the iterative version of DFS. I'm going to copy a bit of code because this part is going to be exactly the same. So I initialize a visited array, but now instead of enqueuing and instead of using the queue, I use the stack. So now I push instead of enqueue the start node. And while my stack is not empty and this is stack, first off, V becomes peak stack of content and I pop, okay? And then allow me please to just copy a bit of code. Actually, no, I won't because it is a bit different here. Now, if V is not visited, if visited of V equals to unvisited, then first off, visited of V is marked as being visited, okay? And then I get all the neighbors of V, and this is this thing I do copy from here. I get all the neighbors of V and the number of neighbors, and and here is maybe a bit more. Here's a bit more of a tricky part. I start off from number of neighbors minus 1, I is bigger than or equals to 0, I minus minus, and W, oops, I already have it, W equals to neighbors of I if visited of W is equal to unvisited, then I push W. And finally, here I print out, oops, printf. I finally print out V plus A. Now, question. Why did I do this? Why did I start off like this? Why didn't I simply go from 0 to number of neighbors? Can anyone answer?
Because it's a stack and we begin from the top of it.
Come again? Can you repeat that, please?
Because it's a stack and we begin from the top of it.
But that does that really make a difference here? I mean, I already pushed them from the stack here, so does this really have anything to do with the stack?
We will push them to the stack in the reverse alphabetical order so that in the end, we will have the first one in the alphabetical order at the top.
Yes. Yes, basically, yes. Okay. Let's see what we obtain by doing this. And here, just for the sake of, I'm gonna be doing this. Oh gosh. Okay. Now, the DFS finished and the result is GBACDFE. Did we get the same thing? GB. FEACB. Okay. Well, apparently we didn't get the same thing. Let's try this out. Let's put the 0. GDFECBA. GDFEACB. What? What is going on? Must have missed something. It's most likely I'm missing it here. So let's go through the pseudocode and see what I'm missing. So we have this. While our stack is not empty, over here, we pop the top and V becomes this, okay. And in case we push all the neighbors of V in the stack that are not visited. And so in case V is unvisited, but didn't we already, yeah. Yeah, so yeah. We mark V as visited and then get all the neighbors of V, and then for each neighbor of V, I chose this in the reverse order. V becomes, so W becomes the neighbor's I, so this comes as the last one, and if W isn't visited, then we push it to the stack. You know, I wrote this code quite some time ago. I'm curious why I wrote it like this. Puzzling, isn't it? But I tend to believe I missed something here, actually. Let me just double check. Yeah, I did. I did miss something here. This is not right. Clearly, this is not right. Because I always have in depth first search, I always need to go, well, in lexicographic order, I always need to go to the first neighbor, which is not visited. So let's just redo that a bit. I don't know what exactly I missed, but I did miss something. So if we start off from G, our first neighbor, unvisited neighbor, which gets visited is B. And then we go from B to the first unvisited neighbor of it, which is A. And then we go to C, and then we go to D, and then finally F and E. So let's go through that again as to make things clear. We start from G and we get G's, all of G's neighbors, and that's B, C, and D, but we don't mark them as visited, not like this. We first mark B as visited, and then we go to get all the neighbors of B and mark the first one as visited, and then the stack now contains A on top, and we pop it, and then we mark all of A's, we get all of A's neighbors, and the first one, which is unvisited, is C, and then we start off from all of C's neighbors, and the first one unvisited is D, and then we go to from D's, we get all of neighbors of D, and the first one unvisited is F, and then finally we reach E, and the outcome should be, again, GBA, CDFE, GBA, CDFE, and that is correct. And this is what I was missing, and it was missing from here, not in the actual code, so this is correct. This is finally correct. Okay. Okay. And a more clear maybe version of DFS is actually the recursive one. And I think we have too little time, and I'll need to send you another link. We have 5 more minutes. Actually, we can squeeze this here because it's shorter. Now I'm gonna copy a bit of code from here, and this visited array is common in all of the traversals. And here I just have to call DFS recursive start node and visit it. And that's it. This is basically just a sort of like a top level function, which calls the recursive one. Because I need to first initialize things and then finally call the recursive function. And in here, things are a lot shorter. So we start off from initializing an I, and we mark our current node as being visited. Finally, we get all of the neighbors, and these are common. I can just copy the code. We print our current node. So we do this, v plus a. And for all of the neighbors, so I equals to 0, I smaller than number of neighbors, I plus plus, or is this reverse? No, it's like this. Neighbors of I, and that's W, and if it is not visited, if visited of W is equal to unvisited, then DFS recursive of W and visited. That's it. And let's just call that function as well and see if we get the same thing. Okay. So GB, this is the first, and I'll make it bigger. This is the BFS, this is the DFS iterative method, GBHCDFE, and this is the recursive one, GBACDFE. It's the same. So that's fine, it works just fine. Okay. Why is my internet connection unstable? It's not. Okay, any questions here? Because we have 2 more minutes of this session and I'm not gonna prolong it. No questions?
Can you add this go to Git, or is it already
If it's
added?
not already there, although I think it is, I'm adding it right after, so you'll have the code.
Okay, thank you.
Available. Sure, anytime. So if there's no other questions, your homework will be to manage a graph representation with lists instead of matrices. So instead of having a matrix like this, you'll most likely have a file with a list of some sort. And then you'll have to switch between list representation and matrix representation and back and forth. In the lab, by the way, you can see the reason why you would be using a list representation versus a matrix representation. Am I looking at, yes, I'm looking at the right thing, an arc, a path. Also representation methods, you'll see that which of the 2 representations is best. An adjacency matrix would be useful when the presence of or absence of an arc is frequently tested, and then the list is more, it does make better use of memory, but is more difficult to find arcs if you need that operation quite often. That's about it for today. Next time we will be doing some graph algorithms. I think it's going to be Dijkstra and Kruskal, something like that, but we'll see that next time. Take good care of you guys and stay healthy and stay safe. All right. Bye-bye.
Bye, bye, bye.
Thank you.
Bye.
Bye.
Bye.